My name is Bilal Bugaje, a PhD student from the University of Nottingham. I will be presenting on the topic, Simulating Bottom-up Supply-Side Residential Energy Systems with Nonlinear Conversion Efficiency, a System Dynamics Approach. First, let us explain some terms in the title. Supply side refers to availability of energy. Bottom-up simulation focuses on technical operation of energy technologies, also known as the engineering paradigm. Residential energy systems are discussed within the context of community energy planning, which has three phases with distinct groups of methods. Looking at the groups of methods in each phase, is it possible to go from this to this, where a systems approach like system dynamics might cater for the needs of the different phases? This study focuses on a subsection of simulation models in phase 2 and asks the question, could there be a valid simulation model of SD, a valid SD simulation model of supply side from the bottom up? The aim of this study is to demonstrate a valid simulation model from the bottom up using SD. The case study used to validate the model is Project Sensible in Nottingham, from which specification of some power devices were obtained, as well as measured data from residences that were part of the project. The measured data will be compared with results from the SD model. The modeling process looks like a serpent going through the 4 columns. But what is important are the 4 columns. The first column is the input sources. The second is the modeling stage. The third is the output from the modeling stage. And the final column is the validity tests. Validity tests are an important contribution SD could make to other fields where systematic validation is not explicit. Here, we see how SD concepts relate to model components, features, and benefits. You may refer to the full paper for details. Next, we will look at conceptual models of residences from Project Sensible, having different composition of supply sources and battery. This is a conceptual model of the residence with grid and battery. There are 3 features of the models we should pay attention to. First, energy conservation, illustrated by the material link, which are the double arrows. Second, causal relationships or causal connectedness, illustrated by all arrows, including the single arrows. Third is modularity, which will become apparent shortly. This is the residence with grid, battery, and PV. And this is the residence with grid and PV. I hope the modularity is clear. Next, we look at the residence with grid, PV, and battery, but this time with loss from modeling conversion efficiency. This model is similar to one we have seen, but notice the stocks that account for energy loss from the conversion efficiency. The conversion efficiency is a nonlinear function from the datasheet of the inverter's manufacturer. Next, we look at the behavior of the model systems. The left graph shows the electric power import from a residence with grid and battery. The graph compares the measured values of the residence in red to this SD simulation in blue. You can see that the behavior matches quite well. The right graph shows charging power from a residence with access to grid, battery, and PV. But this graph compares SD model without energy conversion in blue to SD model with energy conversion in red. Given the scales of the graph, given the scales of the graphs, the difference is not clear, but the SD model with energy conversion is always less than without. The loss due to energy conversion, as well as the errors or the differences in the left graph, are also discussed in the full paper. Next, we revisit the research question, which is, could there be a valid simulation, a valid SD simulation model of supply side from the bottom up? The model has been found to be valid. There is further work to be explored to find out about how SD can contribute to the disjointed community energy planning process by integrating the models into a supermodel. Thank you.